All right, so in this lecture, we are going to talk about master-slave JK flip-flops. I can zoom in this, just maximize the window. So JK master-slave FF or master-slave JKFF. So this is different from the one we learned, and this is actually the most practical one people have been using in real life. And this one is edge triggered. So which means it's not being triggered by the level, doesn't like the ones, the SR flip-flop like we learned just now in the previous video. Whenever the clock is on, all the signal is going to be will be passed to the latch, which is not really practical because you don't want to that happen when you have a clock. You just want this one to go there as an edge, then just stay there, don't change at all. Okay, you don't want anything to be changed other than at the edge. This one has that benefit, only allow data to be passed to the latch at the edge. Okay, so how that works? You just need two SR flip-flops. So that's the first one at the output. And there's the first clock. Then this one, that's a clock in the front, at the front. And then feedback from here all the way to here, feedback all the way to the input. And now you have J and K, right? That's a clock. And so that's the first clock for the input, and we invert it for the second stage, right? So that's a master slave. That's a master, that's a slave. Okay. You have J and K, you have clock. Keep in mind that you can find out whenever this one is on, it's getting inverted, this one is off. So it disabled the slave, which can only perform like a memory. Okay, so which means when you have a data to be passed to here and be stored here, this one is closed. And only when at another edge, this one is being closed and this one is being enabled, and the stuff can pass it. This is how it's like looks like two steps, right? So for example, when you have a rising edge, so the data is being passed to here. However, here is disabled, so they can only reach here and stay there. Okay, and the next you see this one has a falling edge, and after getting inverted, you got a 1 here, so this part is enabled, so the data can go through. So when the data is going through to here to the output, this one is disabled, so the input won't affect the result here at the output because there are two steps. Okay. It's like a buffering. So this part is like a buffering area. You store something here temporarily and then close the door and then deliver that to here. Okay, things like that. And there are some properties I need to add to it as a description. Advantages. So Q changes state. Only at falling edges. Okay, that's advantage. And behavior. let's write it down in case you cannot remember that. So if J, K are different, okay, which means JK has 1 or 0 or 0 or 1. So which means they're different. And Q takes J at the next clock edge. So which means actually this it's same as the SR flip-flop. You know, when for the JK flip-flop, the J, whatever J is going to be passed to the output. You know, because J, you know, it's actually S. This is R. It's making sense because remember I think we summarized this previously. So think about that. Since S is set, right? So when S is 1, you are setting the result to be 1. When S is 0, which means R must be 1, and then Q is being reset. So you can find out actually S and Q are always the same. It seems like you are actually passing whatever is being stored at J to Q. So it looks like you are passing J to Q. But actually, you know, it's kind of, you're not. They're not the same stuff, but actually they're the same voltage. It seems like that. It works in that way. Okay. And S is J, right? S is J, R is K. Okay. That's why we say this here. And then another one, the second one, behavior. If JK are both low, no changes. And why is that? When JK are both low, 0, 0, you disable these two NAND gates, you got a 1, 1 here. So it's 1, 1 will memorize whatever has been here. You know, so that's why there's nothing will be changed. The third one, if JK are both high at the clock edge, it toggles. Why it does that? So when JK are both high, whenever this one is being passed to here, so you are passing 1 to here, because it's not affecting the result, right? So that's why your output here will be, because you can see that output will be from here will be delivered to this part, and this part will be delivered to this part. So every time at the clock edge, so for example, if you have 1, 1, okay, if you have JK to be 1, 1, but previously Q and Q bar are different, it's 1, 0. So 0 will be delivered to here, 1 will be delivered to here, and then you have 1 here. So 1 and 1 and 1, you got 0. And here you have a 0, you have a 1. So 1, 0 here. And 1, 0 will be directly, so 1, 0 here is here's R. So you are resetting the result here. Finally, what you are going to get is 0. So 0, 1, right? So 0, 1 right now. But for this SR latch, 0, 1, so here is R. So you are resetting the result, you got a 0, 1. But previously, we assume we had a 1, 0, right? You know what I mean? So that means every time, if you have JK to be connected to voltage high, whenever a clock edge, at the clock edge, which means whenever this one is being enabled, it's actually a falling edge triggered flip-flop. So whenever at the falling edge, the result will be toggled. Okay, so since this has been recorded, so if you didn't follow that part for this statement, you can replay the video. But actually, you know, you can run all these digits by yourself. Or you can directly just remember that. This is the structure of this JK master slave JK flip flop won't change at all for, hasn't been changed for 50 years, and in the future probably won't be changed at all. Unless people are not using CMOS anymore, they're using something else. Okay, but the logic is the logic. Will keep the same. All right, now we know these properties. So what we are going to do is look at some of the digital waveforms and find out the result from the waveform. Okay, let's look at one example. It's actually 11.7 on the textbook. Complete the following timing diagram for the flip-flop of figure, of the following figure. So that's a rising edge triggered JK flip-flop. Okay, so here is a clock waveforms here, and you have a clock. 50% duty cycle, perfect clock. Okay, and then you have J, you have K, you have Q. Given that J will change the state in the middle of the clock, and then keep going until here in the middle here, and then go back to 0, and at the fourth one in the middle, go up, and here go down here. So for K, it used to be this and becomes this, and get over here and then go back to 0. Okay, so what is Q? So all these signals are given. So these 3 signals are given. So what's a Q look like for the master slave JK flip flop? Okay, you can refer to the schematic we just drew here. All right, but keep in mind, it is just the falling edge triggered. Rising edge is a rising edge triggered. So it's going to happen at the rising edge. So changes will happen here at the rising edge. And remember that. So when you have so at the rising edge, what the JK flip flop does is at the rising edge, it's going to pass whatever at K, whatever at J to Q. That's it. That's what the master slave JK flip flop does. But the prereq is you have to have your JK, the signals to be different. If they are both zeros, then it's a memory. It's just following the previous state for Q. If they are both ones, you need to toggle your signal. So this is the only 2 things you need to keep in mind. So now let's see. When you have 0, 0, let's see, assume the initial state for Q is 0 here. So at this rising edge, it's 0, 0 is going to memorize the previous state until the next rising edge, right? What's going to happen? You have JK to be 1, 1. So remember that we summarized everything in the previous page. Your signal will be toggled until the next rising edge. And now here, what's going to happen? You have JK to be 1, 1, and your signal need to be toggled. So you need to put it down to 0 again. And here, your JK are different, and now you get a chance. Now look at what is J. J is 0, so your signal need to be 0. Now here, JK are different, and your J is 1, so your signal need to be 1. And JK are both zeros, you need to keep memorize the previous state. So this is how you find out the final result from this master-slave JK flip-flop. And there are applications, pretty important implications for JK flip-flops. That's why we learn it, right? And now the first one I want to introduce to you guys is a counter. So you can use the toggling function of the JK flip-flop to design a counter from it. And you'll find out what that looks like. So the circuit, for example, this is a 2-bit counter. You have J, you have K, and you have a clock here. For example, this is QA. And you have another one which is the same function block. You have J, you have K, you have clock, you have QB, and then J and K, you connect all of them to logic 1. So which means 5 volts, right? So you have all the J and K's are 1s. So the only thing these two flip-flops can do is just toggle the output. And now you use QA as a clock for the next stage. Okay, so whenever we have a little bubble here for the clock, that means it's a falling edge. It's a falling edge triggered. That's why it's a bubble. It's a falling edge. Triggered, master slave. Flip-flop. Okay, keep in mind. And now you definitely have a clock for this guy. Right? And now let's see what is QA, what is QB. Let's take a look at the signal. We have a clock, definitely. The clock looks like 50% duty cycle digital signal like this. Okay, and you have your QA. Since it's a falling edge triggered, so the things only happen at the falling edge, right? And now you have your QA in the beginning to be 0, and until this falling edge, because it's a toggling flip-flop. So actually, they have a name for this kind of flip-flop when you short both J and K to 1. That's actually called T flip-flop. Probably it's a toggling flip-flop. Okay. And now for this for the output for the first T flip-flop, it's going to be toggled, and until the other falling edge is going to be toggled again and be toggled, be toggled, be toggled, be toggled, be toggled, be toggled, right? And now QA is performs as a clock. If you see that, QA is actually being connected to the clock signal for QB. So now QA is a clock for QB, but with a slower frequency. And now let's see. So QB in the beginning is 0 because nothing is being connected to QB until the first falling edge. It's going to be toggled and toggled, toggled, toggled. All right. And now let's see. If we look at this part, it's 0, 0 for these 2 bits, and then 1, 0, and then 0, 1, and then 1, 1, and then back to 0, 0, and then 1, 0, and then 0, 1, 1, 1, 0, 0. It's like it's cycling and following a certain specific pattern here. Actually, you can see that it's counting, right? 0, 0, 0, 1, 1, 0, 1, 1. And then come back to 0, 0, 0, 0, 1, 1, 0, 1, 1, right? Just keep going. So now, let me know which one is the LSB, which one is the MSB. Since it's counting from 0, and then 1, 1, 0, right? So apparently this one is LSB, this one is MSB. Okay. Now you just use 2 T flip-flops to build a this is 2-bit counter. Right? That's what you just got from this master slave flip-flop. So you may be wondering, hey, it's 2-bit, right? Our computer system has like 64 bits. So you can actually stack them together to make more bits for that flip-flop. For example, you can have this one here, here. That's a 3-bit, right? You can add more, but I just show you this as example so you know how to do it. JK, JK3, JK flip-flops, and all of them are folding edge triggered flip-flops. And what you need to do is just connect everything to 0, to 1, right? To make it to be a T flip-flop. And then you just use the first one as a clock, which is the real clock, and all the rest of them are being triggered by the result from the previous stage. All right, so that's a 3-bit counter. The digital system is pretty simple. You just put them together, you can form a complicated digital system. Okay. And there's another application for this master slave JK flip-flops, actually edge triggered flip-flops. So it's called shift register. I'm going to state another new page here. Number 5, page 5. So shift register. So that's why fundamental logic is the prereq for a microcontroller, for embedded systems, because it's super useful. You can see we are looking at the internal structure for all these logic blocks, and you are going to use them a lot in all this design for microcontrollers, all this really fun design later on. You have to use it. But it's important to learn it here so you understand what's going on inside, right? So for the shift register, there are 4 types of shift registers. So the first one is called serial in, serial out, so which is SISO. The structure looks like this. If we have 4 D flip-flops, DQ, 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 and it's a falling edge triggered, right? And you have a clock for everyone. It's going to trigger all of them at the same time. And you have a serial, for example, you have this kind of digital signal. It's 0, 1, 0, 1, 1, 0 or something. Then at every falling edge, the serial data, which means it's in one signal line, will be passed into that SISO, and finally you are going to get the signal here 0, 1, 1, 0, 1, 0, like this, right? So see that 0, 1, 1, 0, 1, 0, things like that. So you will see something like this later on. No, actually not, because all the signals these ones are in first, and they will be, you'll see the same order. It won't be mirrored. Same stuff. You'll see that at the output. And now let's look at another one. It's called serial in, parallel out. How do you do that? Serial in, parallel out. DQ, 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 and falling edge triggered. Clock. Serial in, right? Serial signal going in, and parallel out. So the final result will be a 4-bit binary number here in this application for this specific shift register. So the serial number being shifted in there, boom, 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 and then boom, being delivered in a parallel form at the same time. So that is the second one. And we have a third one. And since we are not using that too much because it's not making too much sense, so you just know that we have the third one, which is parallel in, parallel out, and you have the fourth one, which is parallel in, serial out. So this one is actually, and you can see this a lot. And we have a pretty interesting design here to show you. You'll see this in your homework or exam in the future, so pay attention here. So we add more function to this shift register, which means I can load the data and then shift out the data. It's a little bit more fancy here. So you have two signal lines. That's an inverter. You invert, so signal is getting inverted, and that's a shift or load control line. And now later on you'll let me know which one is load, which one's shift. And we have D flip-flops, 1, 2, 3, 4, DQ, 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 falling edge triggered. Okay, clock. And your data, look at that. The function is you can load the data at the same time and then shift them out. It's something like this. Boom. Parallel in and serial out, right? Parallel in and serial out. So you have the first one as you couldn't change the first data, since you have to have a data for the first one cannot be from nothing, from the air, right? So you need a data line for that. So that's directly just a wire, just a data line. However, for this one, there are options for these lines. And what are they? Let's think about that. So I have a two control wires. I can choose to load or to shift, right? But in the beginning, I need to load it. And then, so which means the data should come from here. And then when it's being shifted, the data is coming from here. So which means you have two paths for the data to be loaded to here. So which means you need an OR gate first to connect to that. And the OR gate will have two paths. So one is from here, another one is from the data line here. So how can you do that? Let me see. So since we need a control wire to control that, we have B1, B2, B3. So these are the data line available, right? That's the data being here, ready. And if you give a 1, for example, you want to use a 1 to load, or it doesn't matter actually. So for example, let's do 0 to load, 1 to shift, right? So 0 to load, which means 0 is being inverted, and you get a 1 here. So 1, you want a 1 to load the data, and you need an AND gate to connect to there, and you need the load signal to enable the NAND gate and the data line to the AND gate. Okay, so that's how you can use 0 to enable the AND gate and load the data to here. And now let's see, if we want to shift it, we use another AND gate. We want to use 1 to shift it. So 1 is the control wire, and to shift, which means the data is from here being delivered to the AND gate and through the OR gate and being delivered to the next stage. It's the same thing. Right? You need the OR gate first, and then you need the AND gate, and so data line is from here, and you want to use 0 to load it, and data line is from here, you want to 1 to shift it. Same here, 2, right? AND gate. Sorry, I didn't leave too much space from here. The data line, I want to use 0 to load it, and the previous data ready to be shifted, I want to use 1 to shift it. Okay, this is just to show you a really simple example to how to design a digital circuit using flip-flops and also the combinational logic data gate, digital logic gates. All right, let me see if we have. Yeah, I think that's everything I want to introduce to you guys in this video. It's been 30 minutes. I don't want to make it too long. And we will probably have homework assignments for this one to build up the counter or a shifted register using LDSpice. I do not think that's a big problem because you can have, I have already showed you all these logic gates and circuit schematic for these logic blocks. You just build them in LDSpice, and if you have questions, welcome to send me an email to ask. And all right, thank you for watching, and we'll see you in the next video.